Hello everybody, this is the lecture for the first laboratory session, Physical Properties of Fluids. So, during this experiment and lab session, the properties of two fluids will be tested, water and kerosene. The next properties will be tested, density for water and kerosene, the specific weight for water, the surface tension for water, and the viscosity for water. After this lecture, you should watch each of the videos for getting all the data from the laboratory for reference. So, just like solids, liquids also have their own characteristic density. The density will be equal to the mass divided by the volume, with units of kilograms per cubic meter. The volume of a liquid can be measured directly from a graduated cylinder. That means that in the graduated cylinder we will put our sample, which in this case is either water or kerosene, while the mass of water will be obtained from the graduated cylinder and the balance. So in the cylinder we have both the weight of the cylinder itself and the weight of the mass of our sample. The density of the test fluid is to be found by weighting a known volume of the liquid using the graduated cylinder. The cylinder is weighted empty. Then it is filled to a certain volume according to the graduations on it, and it's weighted again. The difference in weight divided by the volume gives the weight per unit volume of the liquid. By appropriate conversion, the liquid density is calculated. The mass per unit volume, or the density, is thus measured in a direct way. So, the objective of this laboratory part is the ability to measure the volume and mass of two liquids, to calculate their density, and explain that since any volume of water always has the same density at a given temperature, that density is a characteristic property of the fluid. Also, the known density of the kerosene used in this laboratory session is 775 kilograms per cubic meter at room temperature. This is a table in which you will need to get the data from the experiments. Again, since you won't be able to perform the experiment, this is the table that you should be able to fill it out in the experiment, which is we have 3 trials. We will do 3 trials for all the experiments in this session. Then we have the weight of the water, which is the weight of the water plus the cylinder minus the weight of the cylinder. Then we convert that weight of water from grams, which which our scale give us, and we convert it into kilograms. And then we have the volume. In this case, for these trials, we will use volumes of 100, 200, and 250 milliliters. Then we convert that volume from milliliters to cubic meters, and then obtaining our density. This is the same way for the kerosene. So we will do also 3 trials for the kerosene, obtain our weight, convert it into kilograms, and our volumes of 50, 75, and 100 milliliters. And we get our volume in cubic meters and calculate our density. Next, we have the specific weight. The specific weight is weight or gravitational force per unit volume, which the specific weight will be the weight divided by the volume. In other words, will be the density multiplied by the gravity. So, the specific weight is dependent on the acceleration of gravity, which is 9.81 meters per second, and hence varies with location. We know that in different locations of the Earth, we will have different gravities, having a much higher gravity in the poles and a lower gravity in the equator. Also, the specific weight varies with temperature. With more temperature, it gives us less specific weight. So think about this. Molecular activity and spacing between molecules increase with temperature. Fewer molecules exist in a given volume of fluid as the temperature rises, reducing the specific weight as well as the density. So, the specific weight also can be calculated by the specific gravity of the fluid. The specific gravity is the ratio of the density of the substance to the density of water at a specified temperature and pressure. So the specific weight will be the specific gravity multiplied by the density of water. We can get the specific gravity from the hydrometer. So for the specific gravity experiment, we will need a hydrometer, which is this instrument. We will need a cylinder and the fluid. So the first step is to trial and error until we choose the appropriate hydrometer bulb that floats. For the hydrometer, I will show you in the experiment videos. We have different hydrometers with different specific gravities for different densities of the fluid. So if a density of a fluid is very high and then we want to test water, we will need two different hydrometers. We have to trial and error until we choose the appropriate hydrometer bulb that floats. Then we allow the hydrometer to stabilize. Once it floats, we have to let it be for a couple of seconds until it is stabilized. Then we have to read the specific gravity directly from the scale and read at the bottom of the meniscus. After we locate the meniscus, we have to take readings of the fluid, and the scale is read from top to down. And also the specific gravity, the known specific gravity of water is 1.0. This is our table that we will be using in the laboratory to get the specific gravity of water. So as I said before, we have three trials, and then we do 3 trials calculating the specific gravity of water after we find the good hydrometer. And then we multiply by the gravity and we get our specific weight. For that, for all our specific weights, we are also need to obtain an average from our 3 results obtained in the experiment. The next experiment we will be performing is the surface tension. The cohesive forces between liquid molecules are responsible for the phenomenon known as the surface tension. Apparent tensions effects between surfaces of liquid with another fluid or solid depend on intermolecular cohesive and adhesive forces. A force pulling inward at the surface of a liquid tending to make the surface area as small as possible. To explain a little bit better about the surface tension, on the interior of a liquid, here water, a molecule experiences attractive forces equally in every direction by neighboring molecules. The resulting force of value is 0. So for example, we have here a molecule of water, and then we have here their neighbor, also a molecule of water. This molecule has attractive forces in all directions, also will this molecule have, and they cancel out, having the resulting force value 0. Then a molecule located on the surface of a liquid lacks some neighboring molecules and thus experiences an imbalance of forces. So for example, this molecule of water is at the surface, then lacking some neighboring molecules, which are these two, the missing water molecule. So it will have 4 water molecules in the water and 2 missing ones, and then experiencing an imbalance on forces. Then the attractive forces of a molecule to its remaining neighbors are stronger on the surface of the liquid. As a result, a force F develops that is directed at the interior of the medium. Therefore, these four forces will be bigger than these two, and we have this result here, and the result will always aim towards the surface of the liquid, towards the interior of the medium. That is why we have the force pulling inward at the surface of a liquid. So in other words, when you see a drop of water and you see that the water is round, that the drop of water is kind of round, and you will think about it and say, okay, why is it round? Why is it not completely flat in the surface? This is because when molecules of water gather together, they work more or less as a magnet. So they clump together and they form this surface tension force, which all the molecules and the molecules in the surface or at the edge of the drop in this case will create this force towards the drop, making the drop smaller and smaller, trying to make it smaller. Another example is, for example, when you get water from the tap, from the sink, you will see a couple of droplets wanting to drop, but they don't do it, so they are just floating. That is because the molecules of the water are trying to attach to each other so hard that they can overcome the weight of the gravity, and they can stay into the sink in this example and not falling because of surface tension. The tension is bigger than the force applied due to gravity. So for the surface tension experiment, we will use a 250 milliliters borosilicate glass capillary tube with a 0.5 millimeters in diameter, which graduated from 0 to 10 centimeters in 1 millimeter increments. And then a larger tube, which is this one, open at one end with a vent at the top and a hole and a stopper. This is the vent and this is the stopper. So the steps to get the surface tension is to place a quantity of the sample in the outer tube, in this case water, and then insert the capillary tube with the stopper into the outer tube, such as the lower end of capillary and the scale are partially submerged. So for example, the capillary tube is inserted here and we should need to place water until here. The capillary tube has to be partially submerged into the liquid. Then we have to blow into the tube so that the sample moves completely up and down the length of the capillary tube. Then we put a blower in this side and apply pressure, and then all the water will rise to the capillary tube and start coming out from here. Then we have to measure and record the distance between the menisci and the capillary tube and the outer water level. That means that when we stop applying pressure, our water level in the capillary tube will start decreasing until it reaches equilibrium. So for example, if the equilibrium is here and the water level is here, we have to measure the distance between the two water levels. And then we have to repeat the experiment 3 times. And then after getting that distance, the surface tension can be calculated from the rise in a capillary tube, which S is the surface tension equals to 0.5 multiplied by the height of rise in the capillary tube, multiplied by the radius of the capillary tube, multiplied by the fluid density, and then multiplied by the acceleration due to gravity. And here we have the table that we will be using in our experiment lab in order to get our attempts in the experiment. So we have 3 trials, and then we should get the height rise of the capillary tube, which is the difference in which is the distance in the 2 water levels, and we do it at 3 times, and we obtain the surface tension and perform an average. Lastly, we will calculate the viscosity. The viscosity is a measure of its resistance to shear. Consider 2 parallel plates, which are these 2, enough that large enough that edge conditions might be neglected, and place it a small distance apart and measure that the space is filled with the fluid in question. In this case will be water. So we can get U by the application of a force F corresponding to some area A. As we can see here, U is this distance, and we apply a force or F, we get in an area of A in here. Then particles of the fluid in contact with each plate will adhere to it, and if the distance y is not too great and the velocity u is not too high, the velocity gradient will be a straight line. A large class of fluids for the shear, to get the shear stress for a large class of fluids between any 2 thin sheets of fluid may be expressed as, which the shear stress is this, equals to the force divided by an area, or equals the mu multiplied by u divided by y, which mu is the coefficient of viscosity, which is expressed in kilograms per meters per second or Pascal per second. So for the viscosity, another measurement of resistance to gravity. The viscosity is another measure of resistance to gravity. So for the viscosity in the laboratory session, we will use the Abel-Hout viscometer, and we have to determine the time it takes a fluid to flow through the capillary tube, which the viscosity will be equal to K multiplied by the time, which K is the viscometer constant, which in this case is 0.1144. K is the viscometer constant, and then we multiply by T, which is the efflux time. I will explain that with more detail in the laboratory session. So, in order to obtain the viscometer from the Abel-Hout viscometer, here is the Abel-Hout instrument, which it has 3 tubes at the top, which is the 1, 2, and 3. The number 1 is the bending tube, the number 2 is the capillary tube, and the number 3 is the filling tube. Here we have number 4, which is the reservoir. So our step 1 is to fill the reservoir until the meniscus meet the mark. So we have to fill the reservoir with water through the filling tube, and then we have to put water that fall within these 2 marks, between the 2 minimum and maximum fill marks. So our step 2 is to place a finger over tube 1, apply pressure to tube 3 with a blower, and let the liquid reach the center of the valve 9. So when we blow air from tube 3 and put our finger on tube 1, water will go from here, and it will start going up until the reservoir number 9. And then we have to remove the finger from tube 1 and place it into tube 2. So after placing our finger on tube 2, we will have the number 2 tube filled with water. And then our step 3 is to remove our finger and measure the efflux time from M1 to M2. So we have our water level here, for example, and then we have to have ready our stopwatch now, and when we take out our finger, water will start going down, and we have to start our mark in M1, and and our time in M2. So we have to get that time in our experiment. Here we have the table of the viscosity, which again we have 3 trials, number 1, number 2, and number 3, and we will get our time from the Abel-Hout viscometer, and we will get 3 times and getting an average. So lastly, for our discussion, we have to compare our results with the actual properties of fluids. We have to find the error between your values for all the 4 properties for both water and kerosene. So after understanding and performing the experiments, in this case watching the videos I made for you, you will be able to start doing the report, where in the discussion we recall our results, the average value in general, and start comparing them to the known value and explain their variations, such as the difference in temperature. This is also the time to calculate the percent error, which is basically the average result minus the known divided by the known value. If we have a big variation, we can say and conclude that the instrument is not accurate, or there is some kind of systemic error due to some inaccuracy. For example, reading the measurements, getting times with the stopwatch and so on, getting variation in the results with the time. Also, our temperature is different from the known value at a given temperature. That could also generate a variation. So all those special cases, all those variations we will find in our lab and in our experiment, we have to describe it here and discuss the results. And in the conclusions, we can say that the purpose of this lab report was to calculate the fluid properties of water and to compare the measured quantities to their known values. So also in the conclusions, it is not at length and we will not discuss as much as in the discussion section, but we will just give a brief summary of each one of the 4 properties for both water and kerosene. So we will describe we will summarize our results and describe what did we get from all this report. After this slide, I will finish my lecture for this class. Please let me know if you have any questions. I will be available today from 12 to 2:30 more or less. I will be online, and if you watch all the videos, and you have any questions, don't feel free to email me. Also feel free to make an appointment. We can have a 20-minute, 30-minute conversation, or less, 10 minutes conversation via Zoom. I can help you with any doubt you have during the lectures. And also, if you have any kind of feedback for me, this is actually the first time I am doing these recordings like for this lab. I usually do it in person. So if you think that I should improve something, or if you think that something needs to change, please let me know. I really appreciate your feedback or any kind of ideas to make it as smooth as possible. So I will upload all the materials before the class time, and I will be online, and if you have any questions, please let me know. So for the second experiment, we will do the pressure and velocity measurements. So after this lab session, we will have, as I said, 2 weeks to hand in the experiment, the lab report, and then we will have this second experiment and lab session. Also, I already filled up all the groups for each section. So if you didn't complete, or if you didn't have time to put your name under one group, I already did that. So you will have a group already. And feel free also to try to connect with your group classmates. You can create groups and you can talk about it, and you can perform your own results, since you didn't do the experiments, but you can calculate by yourself, and then you can compare your results to your students to double check if you got the same result, and if you got a different result, ask why, or try to compare and put together the ideas you have from this lecture and from the videos. And also you will be able to do the lab report. You can also work together. I know this is not the best thing, like working online and working like with a lot of people with with the report, but try the best to work together and try to put the lab together, even though like one person might have one section and the other person will have another section. It is always good that after we put together the whole report, you will need to read it through carefully and change something if needed, and try to check also consistency. Also be careful about the significant figures. That is very important for these values because we have some measurements and we will have some results from the experiment. So be careful to be consistent in your significant figures and also with the units and with the conversions. Okay, so if you have any questions, again, feel free to email me or shoot me an email. I will be available. Thank you.